Okay, so I'd like to again welcome everyone to Distributed Systems. This is the first lecture, which is designed to be a conceptual overview of the key issues and thinking that goes into distributed systems. I often spend actually a lot of time talking to this particular set of notes because, in my experience, there are many aspects of distributed systems that are surprisingly not so well understood. And I think a big part of this is that, since we're in the modern internet era, we sort of take for granted that the internet is really not this single entity, but rather a collection of networks. It's built with a remarkably complicated set of software services, which come in the form of protocols and programs that implement those services. So, the mindset that you need to have going into distributed systems is that it's really a story about hardware, software, and for lack of a better word, a set of services that go around supporting this rather complex coordination. So one of the things that I want to do right away is to sort of talk about, well, what is a distributed system? So we get some kind of working definition in our heads as to what a distributed system is. And if you look at the two quotes I have here, these are basically two ways of thinking of a distributed system. The first is to think of it as a collection of autonomous computers that are linked by a network with software designed to produce an integrated facility. And the second definition that I'm going to give you is a collection of independent computers that appear to the users of a system as a single computer. These are quoted, but in just about every distributed systems textbook, you'll find this sort of crazy definition of things. In some ways, I think that the way that we define distributed systems here is a bit of a myth. It would be nice if all of the resources that you have in a network system would be organized like a single computer, but the reality is that it is sort of a cobbling together that very rarely looks like a single resource. I mean, we pretty much visit websites that are out there on the internet separately, so we hardly think of one website as being the same computer as another one. Okay, so these are sort of ideal pie-in-the-sky type of dreams that people have about distributed systems. I think everybody still is hoping that one day all of the resources of the internet and other kinds of network systems would appear as one, but it hasn't really happened yet. I like the first definition a little bit better because it basically talks about providing more of an integrated and coherent experience. And I think that this is really in line with the way that people are thinking about computing today. Instead of trying to have this sort of single resource, what we at least have is some ability for us to view and exchange information through established protocols. And then, of course, people can build layers on top of this that allow different levels of integration to be experienced. Okay. So anyway, let's just take a look at a few examples here. I'm not going to go into extensive detail on some of these except to make you aware of why they're distributed. Probably the most famous example, and even one that exists in our own department, is departmental computing cluster. Basically, this is where you have a collection of nodes that are connected together by some kind of network fabric, and then they can be used to perform computations. My own research is originally on parallel and distributed computing systems, primarily focused at computational domains. And so, the department computing cluster is one that goes back several decades now. Corporate systems are another really common one. I mean, especially in major enterprises, you'll see lots of servers, lots of desktops, even dedicated visualization systems. And the third example that is really obviously entrenched in the current era is cloud computing systems. The offerings from Google, Microsoft, and others are really a good example of basically very large federated systems that are even geographically distributed. Google, for example, has server farms on just about every continent except Antarctica, maybe. So that's just a really good overview of like the kinds of distributed systems you tend to see out there. I want to point out there are some that I did not list here that are kind of more niche type interest, like the deep space network. I think one day we're going to see that space will have many different computing facilities distributed even across planets and various satellites orbiting planets. So that's already starting to happen with especially the Mars mission and things like that. Now, obviously, what we're kind of interested in, especially since this is more of a software-focused class, is what are the things we can do with distributed systems. So we see everything from email and news reading, which is kind of the early history of the internet. Modern distributed systems tend to be doing things like supporting efficient file downloads, advanced messaging architecture. Some of the ones in the middle of the list have been around for quite a while as well, but are very good uses of distributed systems. Video conferencing is really coming of age with things like Skype and Google Hangouts. If you think about how these things are working, if you didn't have distributed computing, it would almost be impossible to get any kind of good performance in conferencing. So that is, if we were totally centralizing these services, it's unlikely we'd be able to get efficient video communication, especially as there are more than a few participants. And we're still facing many challenges to make these kind of services work well. We have to operate them at low bit rates compared to what the actual available bandwidth might be at any particular location. Similarly, things like the airline reservation system, which has been around for decades, and the banking system, ditto. These both, make use of distributed technology extensively. Okay, so we'll continue now just by taking a look at some of these figures quickly. So, this is sort of like where it all really started. You basically had LANs that were really kind of like an 80s and 90s thing where we were connecting workstations. These are kind of like dedicated advanced computing and visualization stations, PCs, laptops, which really have kind of merged with workstations since I made this picture. And then other kinds of services orbiting around this, especially login service, print and other types of servers. Now this is becoming surprisingly more pronounced in the modern era. You have things like, if you look at like Loyola, for example, we have sort of a single sign-on type of system that basically allows you to have various levels of access to the Loyola network, much like an enterprise computing network. File services, so these are, in the modern era, these are things like storage networks and dedicated servers for storing large files. And of course then there's gateways to other networks. So this means that LANs connected to other LANs and so on. So that's a typical distributed system because basically everything acts rather independently We'll be taking a look at a number of principles later that allow us to critique whether this is really a good distributed system or not. One thing I want everyone to be thinking about in the class is where are the points of failure in this picture? And really, I think the LAN is one of these things that has to be like bulletproof. And so let's keep that thought in mind as we go forward. A contrasted view of the world is one that remains surprisingly in place in some situations in the enterprise. And in particular, we call these centralized multi-user systems. Now, very few people are actually using dumb terminals anymore. However, we are seeing the re-emergence of what we would call this sort of thin and dumb client. And a really good example of that is with the Google Chromebook, which basically is pretty much an access device only, and it can't do much if the network connection or the terminal connection is severed. But anyway, so if you take a look, there's typically in this type of architecture, there'll be like a mainframe computer that basically multiplexes a bunch of sessions. And of course, then the real question becomes, how reliable is this computer? Well, mainframes are built pretty much with the idea of never failing. They cost hundreds of thousands to millions of dollars, and in some environments, this computer may run continuously for years without ever having to be rebooted. Try that with your own computer, although it's getting much better in the personal computing space. So anyway, to continue along, so there's a lot in common between these. And today, of course, what's happening is that there is a convergence of both centralized and distributed technologies to be fully distributed, but maybe having some ultra reliable components that are in the distributed picture. Like I was saying earlier, one of the famous examples of a distributed system is the ATM network. So this is where you go to your teller machine, and you're able to withdraw, deposit money, and so on. To build this kind of system is enormously complicated. And if you take a look at this picture here, you'll see that a fair amount of redundancy is employed to ensure that the network remains robust and reliable. So knowing these things can really help you. On a recent trip, I went to one ATM, and it was not able to dispense money. Luckily, there were other ones nearby. And of course, they were connecting to different upstream computers to do their work. So I was able to withdraw money. So this picture actually shows how something like that works, because you basically have, computers, one or more, in the case of today's ATM network, that can be contacted to broker the transaction. Ultimately, you're going to the bank that has your money to make a withdrawal and deposit. But even before you get there, you have to go to these computers that control teller machines, and then in the banking system, there's obviously a need for a lot of redundancy, in case something goes wrong, because banking is critical. Being able to get money is critical. So that's basically how banks are kind of using a mix of sort of distributed and centralized strategies. On the very back end, where you see these two boxes here, these are probably mainframes or very high-end computers that are designed for 24/7, 365.25 operation. These other computers here are increasingly very commodity-oriented devices. The teller machines, for example, it's very common now to see teller machines running Linux and Windows I think they still use the Windows embedded /CE edition. So, basically, it is a distributed system. A lot of these lines that you see in the picture are using a mix of traditional Ethernet, but the ones that you see from the teller machines are often dial-up lines. You can actually even hear sometimes these teller machines dialing a location, and then they establish a secure point-to-point connection. And you might say, well, why would you ever use something like dial-up? Well, one of the things that is nice about dial-up is that it's very difficult to intercept the communications, especially if you use a proprietary type of encryption protocol between the teller machine and the upstream computers. Whereas if you did those things on the open internet, they become more susceptible to hacking. Okay. So that's kind of what we call the 30,000 foot view of what's going on in distributed systems. So I'm going to kind of just take you through a list of some of the issues here. And I'll probably do that for another 20 or 30 minutes, and then I'm going to break and do the other half of the lecture, just so it's easy for you to also watch these videos in the future. So let's start by looking at what the advantages are of distributed systems versus centralized, because the advantages are really what make distributed systems, I think, a value-adding proposition overall. And I want to point out that I wouldn't be teaching distributed systems if I didn't think distributed systems were awesome. So that should give you an idea of where my loyalties and opinions lie. But in any event, like I said, the picture is a converging one. We want to have distributed systems be built from the most reliable of components. And that, in turn, will allow the true virtues of distributed systems to be exploited in the long run. So there are multiple advantages to working in a distributed way. The first is obviously one of economics. We know that the price-performance ratio of using any kind of commodity technologies is going to, in the long run, be much better than mainframes. And, you really can kind of see this, right? Because your little laptop is a massively powerful computer nowadays. Especially some of the computers that are coming from Asus and from Apple are real speed demons. This one that I'm using is an Apple MacBook, and it is able to produce high-end video while I'm recording this lecture, and it could even be doing a lot more than what we're doing right now. Excuse me. So the other issue is obviously speed. We get the power of leveraging the collective. If you had 1 million PCs, you should be able to get 1 million times the speed of doing it on one PC. Of course, a little bit of an issue is that you have to communicate over the network to get your work done, especially if you have some complicated tasks to coordinate among many computers. So obviously, we have potentially infinite scalability. So as network speeds continue to improve, especially wider area network speeds, we should expect that distributed systems are going to eventually have their heyday. And by this I mean that will do much more than what they're doing now. Then the next one is geographic distribution. I think this is increasingly becoming an important thing. Especially when you look at the fact that probably one of the weakest links of the entire internet is what's happening across the oceans. A number of companies, especially Google, have recently announced that they're going to try to improve the cable to Asia, because that is one that is really, really having to bear a huge traffic load, and it's also a testament to the growing importance of that part of the world, especially as it pertains to the internet. So, we can take advantage of geographic distribution simply by, locating servers and networks within certain countries. So, for example, Google, which has its Gmail service, there are users who enroll for Gmail in India and other countries, and they need to be able to provide, better data access, especially for your home domain where you're located. So, if everything had to go to the U.S. servers, anytime you wanted to send an email or whatever, this probably would not result in the best performance. So we can do a lot to overcome these limitations of, transoceanic cables, for example, by doing geographic distribution. Obviously, another major advantage of distributed systems is that we are become less susceptible to individual failure, when it comes to the system. So we call this fault tolerance officially, but I want to urge some caution when using that term in general. Fault tolerance, it can be something that is either very simple or very complicated, and many people misuse this term, to mean, well, I detected failure, so I have fault tolerance. Well, detection is great, but does the system continue to work after that system fails? Okay, that's what we're really talking about here. And extensibility, obviously you can grow the network, both in terms of networks itself. You can add more routers, you can add more gateways to other networks. You can even have redundant networks, which allows you to essentially double the communication, or more when the network is operating normally. So obviously we can keep growing it. There are more advantages, that are maybe not immediately apparent, but one of the things that distributed systems allow us to solve is the data sharing problem. If we have, in the old days, we basically had, dedicated servers for being able to access your data. There wasn't really quite as well an understanding of, network file sharing. But today now we pretty much take file sharing for granted, and in fact this is really almost becoming on steroids, with the advent of services like Dropbox, Google Drive, and so on. So our concept of data sharing now even goes beyond individual computers and the operating systems they might be using, even the device they might be using. Device and resource sharing is another great advantage. Everyone likes having their own printer, but it doesn't make sense, especially in a number of situations like your own household where everybody needs to print and there's no need to have separate printers. We should share. So obviously being able to communicate with other systems means that we can get other systems to do work for us. And flexibility here is talking about being able to make certain choices in terms of workload allocation. One of the things that's becoming very common now in distributed systems is to combine them with virtualization, which is something I've actually posted some videos on. But one of the things we can do is we can essentially have a virtual machine that runs on one computer, and then if for any reason we needed to get more computational power, or we needed to fail over to another virtual machine, we could even just do this by having that virtual machine stop itself and be resumed on another computer. So there's a lot of this kind of workload distribution and allocation that is becoming more prevalent in the modern internet. And lastly, extensibility is really, I think, where we gain a great deal, not just in terms of being able to add more hardware in the network, but also being able to update software services even on the fly. So one of the things that is happening, especially in the cloud computing era, as I mentioned, cloud computing is really something that is enabled by distributed systems. So in the cloud computing era, you're able to update the software. We do these things like rolling updates where we can actually update a subset of users and servers, even to try out and test a new software release before making a change that could affect every single user. So these are called rolling updates. Google and other companies are doing just that when it comes to especially cloud services, and taking advantage of distributed systems' unique ability to incrementally add and update resources and software. Well, that was a nice rosy picture, and then one that is mostly good. But there are some very serious concerns that we still are facing when it comes to distributed systems. I think one of the big things is that we still, I would still characterize the state of distributed systems today as there being fewer options in the distributed space compared to what we call the standalone computing space. So there's still an obsession with apps. Apps, of course, talk to network services, but they're largely like standalone applications. Obviously desktop software is still kind of running the show for a lot of needs, and the cloud hasn't been able to fulfill all of those needs yet, especially for really highly interactive software. Good example is right now, I cannot really prepare like a screencast and recording using distributed software. I have to basically use software that's running on the device because of issues like latency and in general the amount of space that I need to do the task. So it's an improving situation, but the reality is software is still, I think, also quite limited compared to what some of the desktop applications do. Another issue is, as I've mentioned, or I should say, as I've alluded to a few times during this lecture, networking is still a major issue. Even though we see companies like Comcast advertising that you get like 50 megabits per second to the home, that's not what goes out of the home yet. It's much lower typically, and there often are intermittent connectivity issues and latency issues working with modern networking. Security is perhaps one of the most serious concerns of distributed systems. In particular, data can be easily accessed through what we call network interfaces. And sometimes this data is not properly encrypted. Sometimes a compromise of the protocol takes place. We've had a very well-publicized attack on the OpenSSL implementation of SSL recently, which resulted in data leakage. It was called Heartbleed, in case you want to know the name of the attack. There's a corresponding concern of privacy, and I think that a lot of times people don't know the difference between security and privacy. Privacy is where maybe all the secure protocols were in place, but essentially somehow someone was able to access someone's information without the actual owner's consent. So this is something that has been, again, also in the news recently, where, apparently, the secure protocols were in place, but somehow people were able to access data through some kind of privacy leakage. So when we're designing distributed systems, especially going forward, we need to really be paying attention to these 4 issues. But the last 2, I think, are among the most important. So if you're developing network software, you really need to be thinking about security and privacy as part of your design. So in any event, let's talk a little bit about some of the general key characteristics of distributed systems now. I'm basically going to be taking you through this list here. And then what we'll probably do is take a bit of a break to the next video. So what is resource sharing? Resource sharing is where you basically have the ability to share hardware, software, data, and other information in a network situation. And in almost all cases, when we're talking about sharing, there is somehow a software component to this where you have a network protocol that allows you to share that information. So anyway, just as examples here, in the modern era, we have hardware devices. Printers and disks are kind of well established, but even now, memory sharing is very much a big deal. A lot of what you have happening in cloud computing actually takes advantage of what are called distributed data structures that maybe live on a bunch of different computers. A really hot device right now is sensors. So basically this includes everything from a camera to vibration sensors to heat, temperature, that is. Any kind of device that basically has a sensor input could be used as a hardware device in a distributed situation. So for example, the kind of domains where they're using this sort of technology, obviously we have earthquake prediction, we have weather prediction, we have environmental monitoring. These are all really important examples of resource sharing. The other thing that's a really important type of sharing is the actual software. So this includes everything that you would expect: compilers, libraries. These are the so-called software development kits, SDKs. Other toolkits, these would be like for example in Unix, the command line utilities. Computational kernels, they're kind of a special version of libraries, sometimes even requiring special hardware support. So this would include things like for doing linear algebra, for doing Fourier transforms, and so on. Of course, data sharing is one of the most important things. Being able to share databases and files in the modern era are 2 of the most important things. A lot of people talk about cloud databases. These are basically the same thing as what are listed here. And the difference being, of course, that you may have databases that are living on many different computing nodes, but it's really the same idea. So when we're talking about resource here, we don't need to get into specific implementations all the time. These are kind of generic concepts, but you may find that the complexity of these things being shared varies with the type of platform you're working on. Okay, so if you're on your own laptop, that's a lot different than being on Google's or Microsoft's cloud. So a really general thing about resources, again, I have this figure from many years now, but essentially, when we're talking about resources, we need to have some sort of management associated with them. I'm going to kind of give an example because it's probably looks terribly vague by looking at this picture, but a type of manager might be like a directory service. So, for example, Microsoft, when you're on a Windows network, they have something called a domain controller that runs Active Directory. So that would be an example of a resource manager that allows you to manage, for example, the login to any one of those triangle resources, and also does things like has roaming profiles for users, being able to find the user's home directory, etc. So a big part of what makes the distributed world work, and this is really surprising considering this idea goes back several decades now, is this notion called the client-server model. So the client-server model is where there are some systems that are running, for example, server processes, and there are more systems typically that are running what are called client processes. Now today, I want to point out also that almost every computer that's out there is in some ways fulfilling both roles. So the distinction between actual client and server is sometimes not one that actually reflects back to the level of the whole system. So you really have to be talking about individual services in order to understand the picture. A really good example of a server process would be something like a web server. So just about any client would be, for example, like someone's desktop PC using Chrome to access a web page on another server. Of course, that doesn't mean that the client machine cannot also be running services of its own. For example, almost every computer would be, at least has the ability to do what's called peer-to-peer file sharing. So, so this means it's a different client-server relationship. So typically, when you're trying to draw a picture of the client and server processes, you have to basically use different labels for each of the server processes. In this figure, we just have M, which is some server process. But like, for example, I would potentially use like W for web service, F for file service, and then of course the clients would use a client program, which we would call F star for the file access client program, and maybe W star for accessing the web browser. Okay, so I would like everyone throughout the semester to be thinking more generally. This is intended to be a simple picture, but when you really look at real-world client-server relationships, you have to think about what are the services out there. Okay, so again, back to the roadmap here. I'm going to basically go all the way through to transparency, and then I will pause for a bit. So the next really important principle of distributed systems is something called openness. And in fact, really, without openness, you could build a distributed system. But the problem would be that there would likely be a lot fewer users unless it was an extremely proprietary situation. So again, part of what I'm talking about here is religious. Most of us who teach distributed systems are believers in an open internet, and that really governs a lot of the way that we teach distributed systems. And I know personally I'd be a lot less excited about using distributed computing if everything were proprietary and there were no way to build new functionality easily around the distributed system. So what do we mean here when we're talking about openness? Well, first of all, that we can extend the system in various ways without disrupting the existing system and services. So this means that even if it's open, there has to be some curatorial or editorial oversight of what new things are being added to the system. I have an actual example of such an organization, which is called the Internet Engineering Task Force, which has played a long-standing role in the evolution of protocols for distributed computing in general. So, so basically, we're mostly talking about the software side here right now. So the two types of things we want to be able to do is to work with the operating systems themselves. That's one type of openness. And then the other is to basically work with communication protocols. In this class, because this is not an operating systems class, it's a distributed systems class, we're going to focus mostly on communication and networking. But there will be some times where we also will take a look at actual operating systems interfaces, especially if it helps us to improve the performance of what we're doing with the network. So, open distributed systems, therefore, are characterized by the fact that we have key interfaces and details of the protocol itself are published. A very famous example, which I'm just going to forward to briefly, is this protocol called HTTP. You probably have heard of it, and even if you have not heard of it, you probably heard of Tim Berners-Lee, who is the founder and creator of the World Wide Web. Basically, this protocol, was developed in the 90s, but really only finalized this version in 1999. So anyway, the other person you probably will be seeing here is named Roy Fielding, who is known for his work on RESTful thinking. So, one of the things that's really nice about these protocols is that they often shed a lot of light into the history of the internet or the network in general. And I would like to encourage everybody to read through this particular document and just get an understanding of how we came to where we are in the World Wide Web. There would probably be a small assignment about this at some point. Okay, so basically that's what I wanted to say about open distributed systems in general. So let's talk briefly about this concept called concurrency. I think and for many people this probably means multi-threading, but I'd like you to kind of suspend your view of the world as concurrency is the same thing as threads. Concurrency really has to do with the ability to execute some task or processes simultaneously. And simultaneously means that if you're on a single system, you probably need to use processes and threads. But when you have multiple systems, then it's very likely that you would have, you could have concurrency just at the process level where there are two processes that are running and they are both actually operating concurrently. So concurrently literally has to do with able to take place same time. Again, we'll talk more about the concept of time later because in a distributed system, the issue of clocks and time is one that becomes more and more important as you try to build network services. So basically, there's a lot of concurrency even when we just focus on executing programs. Like if people run browsers, that's a form of concurrency. Concurrency is also where people are trying to access a service simultaneously. A really good example is like file services. So you don't explicitly think about creating threads, but nevertheless, you are doing something that's very concurrent with respect to other users. So basically, in a distributed system, the opportunities for concurrency are enormous and infinite. And that's what this picture is trying to show you here, is just when you're sitting at your computer, you're doing stuff, other people are doing stuff. That stuff is concurrent. It's taking advantage of services, possibly replicated services. And this allows a fairly high amount of throughput and productivity to take place. So basically, I want to talk a little bit about, what is a major affordance of distributed systems. And again, this is kind of a theoretical point because, it's possible you can get really bad performance in distributed systems when you don't do things correctly. So, a big thing that we'll be talking about kind of generally is how many systems are actually part of a distributed system. So typically today, this is tens of thousands to hundreds of thousands of computers, right, that are all connected through local area networks and the internet. So the one thing that is really important in scalability is that we should not have to be changing the system and software all the time. There are times where we need to update system software globally. Good example of this, which you probably know, is when there are security or other vulnerabilities reported. So this means you may need to change the system software dramatically by updating OpenSSL or whatever SSL implementation is on your computer in the case of Microsoft. And so what are the things that influence scalability the most? Obviously, the speed of the hardware is an important thing. In fluid dynamics, it's often said that, your slowest pipe influences, the flow of liquids, for example. So, if the same thing is true with computing. If you have a really slow client computer, you're probably not going to feel like your distributed system is all that fast. So this is actually kind of an important thing in the modern era where we're moving more and more client software, especially to what we call apps. And so it really points to a crucial need for smartphones and smart devices to be having at least fast enough processing power so as not to create embarrassment. Software itself is crucial. So one of the ways that mobile devices, for example, appear to be faster is they're running an operating system that is pretty stripped down compared to a typical desktop operating system. So this, is one of the I'm giving the mobile as an example here, just to show you how these dimensions of scalability actually affect your perceptions of the mobile experience. Networks, again, this is, an important thing. A lot of times, people think they need to have megabits or megabits, gigabits, terabits of, information flow per second. But really, a lot of that is mostly important when servers need to talk to each other. A lot of the things we do on networks, are fairly lightweight. I mean, the vast majority of network performance that we need today is still for the mundane tasks like email and basic messaging. Of course, I will be shortly experiencing a need for fast networks when I have to upload this huge video to the server. That is the YouTube server. So obviously, this has a significant impact on your perception of scalability and performance. And lastly, storage is perhaps one of the most important things. We still, need to have storage for especially the high end of computing. If you're just writing a term paper, you probably can do most of your work can be done on even a simple old floppy drive. But if you are designing the next aircraft, you need to have file storage and you need to have very fast disks as well. So that combination of things can really influence how scalable a distributed system is. And it is kind of application dependent how you weight each of these categories. I wanted to say more about fault tolerance. This is one of my favorite topics, again, because I often enjoy listening to how people know so little about this topic. And I think it is still an area that is replete with research opportunities. So the thing is, what fault tolerance tells us is how can we cope with failure? In particular, if something fails, can we continue to operate normally? That's what we're hoping. What I would like everyone to think about is just how difficult it is to achieve this. For example, if I lose my computer, then obviously I'm not going to be able to recover very easily. Of course, I can always switch to a different computer. Now, when my computer gets lost, the rest of the internet should continue to work. Thankfully, it does. Now, the other situation is where you lose a key piece of network connectivity. So if I lose the connection from my house, well then fault tolerance is pretty much zero. I can't do anything. Now, if I had two network connections, on the other hand, then I can continue to operate. Now, many of us do. We have like our home internet. We have, for example, 4G or 3G networking. But are we really able to talk about fault tolerance here? And the answer is, in many cases, no. Because, for example, most of us don't have our home network set up to where the router, for example, can switch over to another network. I wish that this would become more common because I've had my work disrupted numerous times in the last several weeks by a failed network connection. So, in order to achieve this, we need to have a very unique dance, if you will, of hardware and software. Without redundancy of the hardware, we really cannot achieve fault tolerance based on our understanding of computing today. And it's very unlikely any further developments will eliminate the need to have redundant hardware. So this means literally your computer has to have redundancy. That is, if your processor fails, there should be another one that could be switched over to. It probably means replicating every component in the system, replicating your network, replicating your internet connection, and so on. So there is surprisingly good progress to report on the rest of the internet, especially because of things like cloud computing. So in a place like Google, if a server gets lost, it's no big deal because the way that the cloud world is working is that they basically keep a copy of your data on maybe 2 to 3 other servers minimally. And then when that server that crashed comes back up, the state of would be basically replicated from one of the other servers that has the latest and greatest data. Obviously, to do these kinds of things requires what's called software recovery. That is, the software must identify that a failure took place, possibly when the system comes back up, and then the system must be restored to a state that is a known good state. To make this class fun, I'm going to be asking you, of course, to be thinking about how how does your system that you're developing support fault tolerance? And what are the design decisions you make? So, in general, with distributed computing, we have to deal with this problem. We know that distributed systems give us the niceties of life, namely being more available. That is, if you have more systems, then the probability of any one of them causing the whole system to fail is lowered dramatically. But on the flip side, it's important that a distributed system also remain coherent and have the correct state at any given time. So this can actually add a lot of overhead to the architecture. Well, anyway, so I want to basically say a few words about one of my most favorite topics in this course, which is transparency. And then we're going to see a number of very specific examples of this a bit later here. I believe I have several. Yes, coming up. Okay, so let's just say a few words about it now, and then we'll be seeing a little bit more about this as we go forward. So there are basically 7 types of transparency listed here. And all of these are, in my opinion, crucial to maintaining the perception of a distributed system as a whole or coherent entity. So, some of these may be more important than others, but, in general, if we don't have these here, it's difficult to maintain the image that, if you remember from the very early part of my lecture, is crucial to being what we call a distributed system. So let's take a look at some examples. Access transparency. This is where basically, whether we're talking about local access or remote access, the operation remains the same. So a really good example of this actually is from file systems. If I read from a file, I don't use a different read function call to read, say, a local file, that is one that's on your, let's say, in your documents folder, versus one that comes from a network folder. Read is the same. Okay, now, of course, the difference is that the read will be slower when it's coming from the network. But if we didn't have a read that can handle every type of thing that there is to read, we'd have a major problem. So that's really one of the most important principles of distributed systems, is to support access transparency. The other thing that makes a distributed system special is location transparency. That is, we should generally be able to be comfortably oblivious to the location of a resource. For example, if I'm accessing a file, I don't really need to know where that file is, as long as that server is responding. Okay. Another example is when I go to a website. I don't need to know where gmail.com is. It could be in US, it could be somewhere else. But as a user, I shouldn't have to think about it. Okay. Now, location transparency is also important for keeping our head on straight. If we had to know all these details about how a resource is accessed and where it's located, well, we wouldn't be able to make use of that easily. And by easily, I mean as a programmer. Like, if I want to be able to do something with a resource and I have to know all these details, I probably will not be able to write the code to access and use that resource. So here is where things, now when we start getting further down this list, the importance in some ways goes up and increases the challenge of being distributed. So one of my favorites is also migration transparency, and that is like if I want to move a resource in some way, I can do it without changing the name of the resource. So again, we have this happening all the time in our department. We change servers, and in fact, I had to change some servers to be cloud-based servers recently. And so all I did is I made a simple change in the DNS entry. So instead of having this point to an IP address at Loyola, I had it point to an IP address that's somewhere in the cloud. And from the standpoint of the users, nobody noticed the difference. Well, they might have noticed one difference. We do tend to have networking go out at Loyola quite a bit. And whereas in the cloud, the servers I'm using haven't gone down in more than a year. So the only thing you would notice is the behavior. You don't necessarily notice anything, though, about the actual resource. So that's what we mean by migration transparency. We can keep the name the same and then just simply perhaps change the lower level details about what that name is actually referring to. If you want to have any motivation for the cloud, the next item, replication transparency, should be of great interest to you. In replication transparency, users can't even tell how many copies exist of the resource. For example, you have no idea how many copies there are of your mail in Gmail, or how many copies there are of your document in Google Docs. So this is because there's a replication factor, and this is used to make sure that even when something goes terribly wrong on one of Google's servers, the chance of you being able to get your data remains high. Now, the next three we've kind of talked a little bit about already, but basically concurrency transparency is, that should say can share. There's a typo here. I'll get it fixed. The ability to use a lot of resources at the same time and without even having to think about it. Parallelism transparency is where one level, in some ways, one level lower in detail, but it's where if we have the ability to do multiprocessing, that we can take these concurrent requests and we can handle them in parallel. The whole idea being to improve the performance that the user experiences. Again, concurrency and parallelism, though, are things that we don't ever want users to have to think about. We only want them to know that it's working well, and one way they know it's working well is when they get fast response time. So these are examples that I think are more performance-oriented forms of transparency than some of the other ones that you might have seen so far here. We talked a little bit about what fault tolerance is, but if you have failure transparency, that means that the user is totally oblivious to any failures that happen in the system. We're getting closer for some things, but we still don't have failure transparency as a feature of modern web-based systems. Really good example happened to me the other day where Facebook had a failure and it gave a notice that something is wrong. So as a user, I was not oblivious to the fact that a fault had occurred, and needless to say, it disrupted my work for the day. I know that might sound crazy, but Facebook is increasingly part of my work life because I'm using it for the discussion group feature of this class. Now, keep in mind that failure transparency of all these is probably one of the highest standards to hold a distributed system to. So naturally, this means that we are not quite there yet. But I do think that as we improve hardware redundancy, we should get to a point where we can do better with failure transparency. So anyway, I'm going to go ahead and stop here for a bit and this will be continued.